My name is Dr. AURO ASHISH Saha. I am a professor at Department of Mechanical Engineering, Puducherry Technological University, Puducherry, India. Today I will be presenting on simulation design framework for multi-scale multiphysics thermoelectric and electrochemical transport in the lightning round presentation. Outline of my presentation will start with describing the abstract, then looking at multi-scale multiphysics simulation and scientific computing, how they are connected, simulation and scientific computing, how it has changed over the years, changing landscapes, phenomenological equations that govern coupled transport phenomena, linearized Boltzmann transport calculator for thermoelectric materials available at nanoHUB, Dualfoil Python application program which provides Porous electrochemistry for rechargeable batteries, again available at nanoHUB. The current framework detail of simulation design for multi-scale multiphysics thermoelectric and electrochemical transport, sample implementation methodology, outlook, and finally the references. nanoHUB, btesolver and Dualfoil resources enable studying thermoelectric and electrochemical transport processes. Simulation design framework for optimizing the multi-scale multiphysics thermoelectric and electrochemical transport in the respective devices is presented here. Simulation. Simulation helps in understanding, predicting and design of engineering systems based on its mathematical description that are governed by fundamental and phenomenological laws following the multi-scale, multiphysics and multi-domain modeling paradigm. Scientific computing, on the other hand, is driving all inventions and discoveries that uses simulation by numerical computation based on a programming algorithm using a computational hardware with application domains and disciplines of energy, biology, computing, finance, etc. Simulations using multi-scale, multiphysics and multi-domain methodology is applicable in many chemical, physical, biological and additive manufacturing systems. Let us look at simulation and scientific computing changing landscapes. So we look at the technology in the first column. What is the old paradigm and how the paradigm has shifted with respect to simulation and scientific computing over the years. Simulation, which was physics driven, has now moved towards data driven. Physics driven simulation, which was carried using computational fluid dynamics approach, is now shifted towards lattice Boltzmann method, wherein we use the multi-scale multiphysics simulation methodology. Data-driven simulation, machine learning, classical machine learning, quantum machine learning, accelerating numerical computations. We have currently GPU, FPGA, ASIC, TPU, quantum processing unit, neuromorphic processing unit, all for doing high performance computing. Software from bare metal to containerized, virtualized, cloud. Scientific inquiry, bottom up. Programming language, interpreted as well as interpreted plus compiled features. Examples are Python, Julia. Algorithm development, corporate community. Product development, experimental to digital twins. Heterogeneous HPC hardware from fixed configuration, energy inefficient towards reconfigurable and energy efficient devices. Programming algorithms, serial towards inherently parallel. Manufacturing is again seen the shift from subtractive manufacturing methodology towards additive manufacturing methodology. Rechargeable batteries, lithium ion towards lithium sulfur based systems. Battery technology from classical battery, where the energy difference is offered by electrochemical changes, towards quantum batteries, where energy difference will be offered by different quantum states. Design of experiments, physical stochastic towards simulation deterministic. The different phenomenological equations governing transport phenomena is shown here, with the flux quantities shown in the first column, namely mass, momentum, energy and charge. So for each of the flux quantities we have transport force field variable, transport coefficient of phenomenological law, equation for the phenomenological law, macroscopic parameter from microscopic interactions, and the resistance based formulation for each of the flux quantities. Linearized Boltzmann transport calculator for thermoelectric materials. nanoHUB btesolver, which is a simulation tool for calculating the thermoelectric transport properties such as Seebeck coefficient, conductivity, electrical, electronic, thermal conductivity of bulk materials based on their multiple non-parabolic band structure information, which uses linearized Boltzmann transport equation under the relaxation time approximation. Many thermoelectric properties for thermoelectric materials are available for simulation, as well as there is a possibility of adding new material library data within the solver interface. Dualfoil porous electrochemistry for rechargeable batteries. nanoHUB Dualfoil.py allows to generate, organize and visualize the electrochemical responses from various rechargeable battery systems with the ability to rapidly set up complex multiscale simulation. Framework details of simulation design for multiscale multiphysics, thermoelectric and electrochemical transport. Thermoelectric and electrochemical transport are complex systems, and simulation are very expensive and time consuming, requiring high fidelity computing. Very often, mathematical approximations such as surrogate modeling is used for analysis and optimization. In simulation experiments, the experimental region is too large and the quantitative factors have many different levels. To maximize the information obtained from the simulation using minimum number of runs, here we describe a simulation design framework based on design of experiments to determine the factors that have the greatest influence on the response of the underlying system. Design of experiment is a systematic statistical method to study the relationship between multiple factors or independent variables and responses, namely dependent variables, under investigation, and it is used to optimize the process or phenomena under study. So we start with one factor at a time method. In a one factor at a time method, the value of one factor is changed and then the response is measured. We keep repeating this process by taking another factor. In a full factorial method, all possible combinations of factor levels are used. Full factorial designs are represented by the form L power f, with L denoting the number of levels and f denoting the number of factors. Fractional factorial method. In a fractional factorial method, a fraction of the number of design points of the corresponding full factorial is considered. Here the objective is not to waste design points for estimation of effects which will not be there. Response surface method. Response surface method is used to model the curvature in the relationship between the factors and the response. It allows to find the settings of factors for minimizing or maximizing a response. Taguchi design method. Taguchi design method is again a type of general fractional factorial design. It is based on design matrix proposed by Taguchi, Dr. Taguchi. A highly fractional orthogonal design so that a selected subset of combination of multiple factors at multiple levels can be considered. Latin hypercube method. Latin hypercube design, the design points are spread uniformly throughout the experimental region. It finds wide application in simulation experimental design as it covers the data space evenly. Implementation methodology is demonstrated using R language which supports design of experiments and analysis of experimental data. For a full factorial method, the library DOE base is used with the following design matrix with 3 levels and 3 factors, 2 factors, sorry, 3 factors. For estimating the interaction effects, the analysis is performed using coded values of the factors. That's why we see here 1, 0, -1. These are coded values of the factor levels. Sample methodology for response surface method uses RSM library. Again, here we are using 3 levels, 3 factors. For determining the optimum operating conditions or to determine the region of factor space in which operating requirements are satisfied, the curvature of the response surface is explored using quadratic regression equation. Finally, we conclude this presentation by looking at the outlook. 3 important points are covered. Using machine learning, linear, nonlinear models in response surface method, integrating experimental design with digital twins, using meta-heuristic optimization algorithms in Latin hypercube method. The references are provided here. I conclude my presentation. Thank you very much.